right, you want to start with the first one?
Yeah, let's start with the first one.
So this one here?
Yes.
Okay. Tom is red-green colorblind, and Henrietta is normal but a carrier. That one, right? Okay, start with that one. So this is what type of inheritance pattern? Yeah, sex-linked, right? Because it says sex-linked. So it's specifically X-linked, right? So it's not on the Y chromosome, it's on the X. So for Tom, for him to be colorblind, all he needs is one. So I'm going to do this. The big C is normal. So I'll say that's normal. And the little c is recessive, which means affected. And remember, female needs two of them to be affected, and male only needs one. It's the only one X chromosome. And again, notice that I made one C much bigger than the other C because I saw that on your quizzes. Some of you wrote uppercase and lowercase, and it looked very similar to me. So I would suggest you probably either pick a letter where the capital letter does not look like the lowercase, like L versus L, or really emphasize the difference between the two, especially when you're counting, right? So Tom is X little c Y. What's Henrietta? She's a carrier. Do you want to open up this can of worms? What's a carrier?
We just asked Mr. Tinto, so we don't need your help.
Wow.
Yeah, we have to do something.
And what did he tell you?
Placed in biology.
What did he tell you?
I don't remember.
We're always right, and Mr. Gray's always wrong.
Is that what he told you? Okay, good. So carrier means she's heterozygous, right? Okay. So when we do the Punnett square, so the Punnett square, this is a monohybrid cross because we're only dealing with one characteristic, one gene. So the male can donate an X or a Y. The female can donate the X with a big C or X with a little c. So let's change the color so you can see this a bit better.
Purple.
So this is X big C, X little c, X big C, Y, X little c, X little c, X little c, Y. So what do we got here? We have one. So these are the males, right? Okay. We have one normal male. We have one affected. I forgot to write male. One affected male. We have one normal female. And we have one affected female. Okay? So the ratio is 1 to 1 to 1 to 1. Right? So the possible genotypes, here they are. And that's it. So we got a 1 to 1 to 1 to 1 ratio. Okay? It's no different than the other stuff, right? Still set up the same way. It's really no different than the autosomal patterns. Yeah, yeah.
Question number 12 on the page.
We're doing this right now. I can come back to that one.
Are you doing all the questions now?
Well, I'm going to go in order. Do you guys want me to do this one? Yeah? Alright. So this one we have to assume that the hemophilia is X-linked also. Now, it says to you that it might not be. You can get hemophilia through an autosomal gene, which means it's not on the X chromosome. But we're gonna assume here that it's on the X chromosome. Okay, so this is also sex-linked. And it's also, this one is also, that's not a good sign. Oh no. I don't know what happened there. Let's see. Don't know what I did. Oh.
You pressed that button, didn't you?
Maybe.
Yep.
So
So educated.
Okay. So we're going to assume this is X-linked and it's also recessive, okay? Yep, still recording. It wasn't the screen recorder that shut down, it was Word. Okay, so Slim is normal. Slim's father has hemophilia. Slim, I'm going to assume this is a guy. So if he's normal, so we're going to do this. We're going to say this is normal, and this is the condition hemophilia. Okay, which I'm just say HEM. All right. So Slim is normal. Slim's father has hemophilia. That information is irrelevant because what does a father donate to his son? The Y. So if Slim is normal, that means he is got a normal allele, and he's Y, right? So XY, he's normal. Now he marries Cinderella. Cinderella is a carrier, so Cinderella must be. Okay, so same thing here. So they have 3 children, Larry, Curly, and Snow White. What would be their respective phenotype? Well, we don't know what they are. We can make a guess. So here is a Slim. Slim can donate an X or a Y. Here is Cinderella. Okay, so this would be a what? A normal female. This would be, oh sorry, she's a carrier. That's got to be a little n. Sorry, little n. So what is she? Carrier, but normal, right? So we have 2 normal females. This normal male. This. Okay, so Snow White must be normal. She has to be normal. But she also might be a carrier. Not will be. Might be. 50% chance, right? That she's a carrier. Okay. Larry and Curly? Well,
Oh, you forgot those.
I know. 50% chance of being affected. 50% chance of being normal. Okay? Again, no different than the autosomal stuff. All right, next question. This one is, yep. Not for sex-linked. Because a carrier means you have to have 2 alleles. And you only have 1 allele on the X chromosome, right? So they either show or they don't. Now this one is a different condition. It's a different disease. This has to do with the deformation of the skeleton. Okay? It affects your growth and development because it's affecting your bones. Now it's sex-linked dominant, so that means that this is disease. And this is no disease. Okay? So it's same setup, just the interpretation is different. Alright, so what do we have? We got Belle has the disease and marries Slim, who is normal. So Slim is what? Slim has to be this. Now Belle has the disease. Slim is getting around with Cinderella and Belle, eh? This guy, man. Alright. So Belle has a disease and marries Slim. Okay, so here's the thing. We don't know if Belle is. Well, let's assume that she's a carrier, and then we'll talk about what if she's not a carrier. So if she's a she can't be a carrier. She can be heterozygous. Remember, a carrier is someone's heterozygous that doesn't show it. So either she's going to be heterozygous. Okay, so let's imagine that she's heterozygous. So here's Slim's possibilities, and here's Belle. So according to this, what are the chances of getting an affected daughter? So is this person affected? Big N means, in this case, big N means what? Disease. So this one's affected. What about this one? No. Okay. What about the boy? Yes, and this one is no. So again, there's a 1-to-1-to-1 ratio, right? That's if she's heterozygous. If she's homozygous, well, we don't know, right? Because the thing is, well, you would just assume she's heterozygous in this case. Well, I would have to tell you something. But if she's homozygous, then there's only one possibility. The kids are going to have to what? Why, Sabrina? Yeah, because you're going to get one of these two alleles, right? So in this case, you don't need to do a Punnett square because you know 100% of the kids are what? Affected. Okay? We can actually figure out the probability of this, believe it or not, in the next unit on evolution. There's a way to figure this out. But for now, let's not talk about that, okay? Because we don't know if she's homozygous or heterozygous, and we have no information from the parents, so we can't work out the probability of them being homozygous and heterozygous. In this case, just assume that she is heterozygous. Okay? Alright, this one. Haha, this is a tough one. Actually, it's not. It looks tough. It's a question that looks tough, but it's not. Once you figure out one little trick, you're like, oh my god, really? That's not a hard question at all. So this is a section called mixed genetics, which means we're talking about the different types of inheritance patterns, not just like the autosomal dominant versus recessive. We're talking about sex length. What are some of the other patterns that you studied? Yep, incomplete dominance or codominance, right? We talked about sex influence and stuff like that, maternal effect. So let's see, and I'm not going to give you a complicated question. So it's not going to be like sex influence or maternal effect. Maybe as a short answer question, but not as something you got to solve. So let's see if we can figure out what the inheritance pattern is here, okay? Let's see what makes sense. We got 2 short-tailed cats, and they produce 3 kittens with long tails, 5 with short tails, and 2 without tails. Now, notice I'm not telling you anything about the inheritance pattern, because you got to figure this out. That's the point of the question. So, how many phenotypes, there's a clue though, how many phenotypes do you see? I see short, I see long, and I see no tail. Okay, so can this be autosomal, a simple case of autosomal dominant versus recessive? Why not, Sabrina? Why can't it be that? Right. In the autosomal dominant versus recessive, you either have the dominant allele or you have the recessive one. There's only 2 possibilities, right? So we know it can't be this one, so it's got to be something else. What do you think it is? What would make the most logical sense? Okay, let's go with blending. So if we're going to go with blending, we're going to pick 2 alleles, and we're going to say what they are. So let's pick one allele. Let's give it a letter. What letter do you want to give it? You want to give it N? Okay. Now what does N stand for? Well, we don't want to use big N and little n because then that would be this pattern. Dominant versus recessive, right? And we just said it can't be that because there's, see how there's 3 possibilities? It's not sex. Was that? So you want to do like an N1 for short? Like this? Okay, and what else do you want to do? You want to do L2 now? Or you mean N2? Okay, and what's N2 going to stand for? Okay. What would no tail be then? Okay, let's see if this makes sense. Let's see if that makes sense. What are your... Oh, I'm sorry. No tail. Okay. I'm not saying this is right, by the way. I'm just... Let's see if it makes sense, right? Okay, so what would a short tail be then? Now the question says two short-tailed cats are bred together. What do you only see here? I only see N1s. So does this work? Does this work? No. So we got to redefine this now. So this doesn't work. So let's redefine it. What could? Maybe the model is right. Maybe just the way we labeled it is wrong. Maybe N1 isn't short. Maybe N1 means no tail. And N2 means long. And then the average of nothing and something very long would be something that is short. Because remember what blending is. It's the average, right? So this would be short. Now, if we do this, we have two short-tailed cats. So that would be N1, N2, cross N1, N2. Okay? And let's see if that makes sense. Can we get all three possibilities? Well, here's one cat, right? Here is the other cat. What would this be? That would be no tail. What would this be? Short. Short. And, well, does that model make sense? Yeah, so that one works.
So how do you get the numbers?
Yeah, okay, so the numbers. Okay, so this is a good question because how many kittens do you have here? 10. Now remember, this is just a prediction. What this says is that 25% from these two parents, 25% will be what? No tail. 25% will be long. And 50% will be short. But does that mean that half of your kittens are going to have short tails? No. Now, in this case, it happens to be 5 out of 10, but don't take these numbers seriously. This could have been 6 out of 10. This could have been 2 out of 10. Remember, these are just probabilities, right? So the point of the question is, can you come up with a way to explain why you get the 3 different phenotypes? So this is an example of what then? This is incomplete, dominance or blending. Okay, incomplete dominance or blending. Okay, so that's number 4. Okay, what about this one? The species Bioelevenus studentis annoyus. Petra. Same thing. Yeah, same thing. Incomplete and blending, I just refer to the same thing. Okay, so. I don't know why they're different names.
Exactly, like heterozygous carriers. This is my biology, is not my game.
All right, so obviously this is a made-up organism. Okay, Bioelevenus studentis annoyus refers to you guys.
That's so rude.
Yeah, break it down. Bio, 11, student, annoyus. That's you guys. All right. So it says blue is dominant to white. So what would this be? Blue. Okay. Blue stripes by the big S, and little s, no stripes. Okay. Now, let's see if we can figure out this pattern. We're going to have a cross between two heterozygotes, which is going to be what? Big B, big S, little s, cross, big B, little b, big S, little s. Now, I can't draw lines, as you know, so I'm going to finally get smart here. So here's one line.
Nasty.
Copy this. Paste. Paste. Probably even a faster way to do this. Move this over here. Move this over here. So a little bit better. Okay, oh, one more. I need one more line. All right. Now I have to rotate it. You know, I'm not going to rotate. I'm just going to draw another. Huh?
Just draw your ugly square. They're still not even straight. Like, I guess not. Oh, yeah.
Oh, quiet.
Right next to the line. You don't need to pick it.
I don't?
You could have made a table. That's annoying.
It's gonna be the best video ever.
Is this annoying you?
Yeah.
Good.
You could always make.
Then I will keep doing it.
Keep on pressing it.
It's like Mr. T when he changed every single word specifically for a bigger font or like Control A. So you don't have to click it anymore. You can just draw another line without clicking insert.
What do you mean? Forget it.
Oh my gosh.
This is good. All right.
Mine's not even straight.
It's straight enough. Okay, so what are the possibilities for this parent? No, I'll make it small. So, big B, big S, big B, little b, little b. The other parent's going to produce the exact same possibilities, right? Because they're both the same genotype. So, okay. So what do we got here? We got B. Let's think about the possible phenotypes, okay?
Sir,
Yes.
big S equals blue.
Okay, so the blue is the big B, and the little b is what? White.
White.
Okay. Big S is blue stripes, and the little s is no stripes. Okay, so what are the possibilities? If you were looking at this bio 11 studentis annoyus, what are the things you would see? Yeah, well, maybe I slipped up. Maybe it's maybe more than 3.
White with stripes, blue.
White with what?
Stripes.
Okay.
Blue with stripes.
Hold on. Wait. Blue with.
Stripes.
Are you sure?
No.
Okay. What would this look like to you? Blue?
Big B, little b.
No. Hold on. Blue with blue stripes. What would it look like to you?
Blue with blue. It literally looks like blue.
Well, it depends.
Exactly.
Different shades of blue.
Okay. All right. In my world, there's only one blue. So I was going to go blue, right?
But I could be right. One that
Yeah, I guess. Same blue.
Like, look, the blue at the bottom of your screen, the blue that underlines your messed up
and the blue.
Same blue. So what would blue with blue stripes look like?
Blue.
Okay. Then we have blue. Another possibility is white
With stripes and white with no stripes.
with stripes,
And white.
Why doesn't that one?
or white with,
Wait, I got a question.
yeah,
Can you still put blue with no stripes?
that's what this is. So it's either going to be blue with stripes, which looks blue,
Yeah.
or blue with no stripes, which still looks blue.
Wait, what
Right?
about-
Right here. That's this. That's this one right here.
Is there only one shade of stripes?
Yeah. Yeah, which is the same as the blue. Because you guys make me blue.
Wow.
Alright, so let's look this up. What would this be?
Recessive.
Blue with stripes, so that would be what? Just blue. There's one. Alright, next one. Big B, big S, little s, what would that be? Blue with, what about this one? Well, they're different color blues, then it would be different, yeah. But in this case, they're the same blue. I'm telling you now. 100% of my world. What would this be? Blue. What about this one? Okay, so we have 4. Guys, it's okay. I'm just saying that the blue stripes are the same color as the blue, okay? So it's okay. It's alright. I understand, but the thing is what you see looks the same as something that doesn't have the stripes because this is for the blue.
The blue with stripes and blue with no stripes.
Exactly, that's what this is. So this is blue with no stripes. Blue with stripes looks the same. So what would this be? So that's 5. What about this one? What's this? What about this one? Sorry, big S, little s? Or just blue? What about this one? They're just going to look what? Blue. So far, they all look blue, right? Okay. What about this one? Blue, right? So if you're ever wondering if we're going to get something different. So this is still? Alright, so we got 10 so far. Alright, what about this one though? Okay, white with stripes. Alright, what about this one?
White with stripes.
Okay, so look, the point of this question is this. The point of is how do you set up a dihybrid cross? Is it any different? Did we do anything different here setting up a dihybrid cross? No. It's a 4x4 grid. We look at the genotypes. We work out the possibilities. And then what's different is how you interpret the results. So all you have to know is how to read the results. So in this case, it's a little bit different, but it's still the same idea. So what's this?
Blue with stripes.
Alright, and this one?
Blue with no stripes.
But it's still going to look what? Blue? So we got 12 so far. What about this one?
White with stripes.
And? So, 12 will be blue, 3 will be white with blue stripes, and 1 will be white with no stripes. All white. Yeah, because to you it looks the same. Alright, 6. What do you think 6 is? Bread maker. What do you think it looks like? What kind of pattern? It's blending, right? So what do you think gray would be? Yeah, or you can just, you don't have to do 1 and 2. If you want, you could say, okay, black is B, white is W. That's fine. It's not a big, you can do that. Okay? So you can say, okay, gray is BW. So if I have 2 gray cats, it would be BW cross BW. So that would be B or W for one parent, B or W for the other. So that gives us black, that gives us gray, that gives us gray, and that gives us white. And the question is, 2 gray cats have 3 offspring, 2 are black. How come I didn't get any gray cats? Nope. Why didn't I get any gray cats? Look at this. Yes, all this is what? This is probability. Or what's possible. Doesn't mean you're going to get a gray cat. You're most likely to get a gray cat, but there's a chance that you won't. Right? There's a chance that you won't. Okay. Next one. So let's be fast here with this one. Table. Let's do a 4x4 table. And then you ask me, why don't you do tables, sir? Why don't you do tables, sir? No, I think I didn't have my cursor down here, that's why. Just thought I'd rip into you guys. Oh, lordy, lord. I thought I picked 4x4. Yeah, you're right. I'm going to do 5x5. Okay. Well, that's going to be a really big square. What kind of inheritance pattern do you think this is? So we have chickens, where we have, Breeza, I think you were working on this question, were you? Okay. So what inheritance pattern is this, Breeza? What inheritance pattern is this? It's a dihybrid cross, but it's a special type of dihybrid cross. Remember what it is? Starts with an E. Yeah. It's where one gene affects the other one. So here's a gene. So you need little I to get color. So the I gene affects the other genes because the other genes tell you what color you're going to get. But if you get a big I, it doesn't matter what the other ones are. You're not going to get any color. So if one gene affects another one, we call it epistasis. So let's work out this parent. I didn't need to do I didn't need to do all of the squares. So this parent is little I, cy, right? So what are the possibilities? So we have little I, cy. This parent can produce a little I with a C or a little I with a Y. Are there any other possibilities? No. There's only two here, right? This parent can produce how many possibilities? 4. It could be big I with big C, or big I with a Y, or a little I with a C, or a little I with a Y. Okay, so let's work out what we got. So we got here, we have big I, big C, big C. Look, what does it say here? Little I allows for color, and big I is what? So, what do you see here? Right, these ones are going to have, it doesn't matter what you put down. No, these 4 here have at least one big I. So they're going to have 4 will be albino. You could fill it in, right? But you know that they have one big I. So that means 4 of them will have no color. The other 4 will, but what are they? So these 2 are little I's. This is what? Red. So 1 will be red. Little I and little I. And this, so C is red, yellow. Red and yellow will give you probably what? So, okay, I don't know if this is blending. If this is blending, that would be orange. If it was codominant, it would be red and yellow. Okay? So I don't know if it's, I would imagine it's probably blending, but it could be red and yellow. I don't know, maybe part of your chicken's red, part is yellow. I have no idea, right? I'm not a chicken expert. So, what about this? That's the same as this one. So that means 2 of them. And then this one is what? 1 will be yellow. So in this case, 50% will be albino, One of the 8, 20, or 12.5%, one of the 8 will be red, one of the 8 will be yellow, and 2 of them will either be orange if it's blending, or red and yellow if it's codominance. But is it any different than the way we set it up? No. Right? It's always the same. Right? Okay. A single gene has 3 alleles. In a diploid organ, how many genotypes are possible? So a single gene has 3 alleles. So that means that the gene, we'll call it gene 1, could be A, B, or C. 2 genes each have 2 alleles. Okay, how many single possible genes? Okay, so I'm going to use 1. I said, you know what, this is going to mess you up if I use 1. I'm going to do it differently. I'm going to do this because you're used to letters being genes, right? So let's stick with that. Let's say a gene is going to be A1, A2, or A3. There's 3 alleles, right? So one genotype could be what? A1, A1, right? What's another possibility? A1, A2, or A1, A3. Or it could be A2, A1. We have that. A2, A2, or A2, A3, because we don't have them here, right? It's just asking for how many possible genotypes are there. So A1, 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 A2, A1, A3, A2, 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 A3, or A3, A3. Because we already have A3, A2, right? It's right over here. So there are 6 possibilities. Yep. Okay, 6 possibilities. Can you think of any other ones? No, right? Yep. Sabrina? Diploid. Di means 2. So everything that we've been looking at are diploid organs because they have 2 sets of DNA. One set from your mom and one set from your dad. A haploid is an organism that only has 1 set of information. So like, now, this is not an organism, but your sex cells will only have 1 set of DNA. Or bacteria will have 1 set of DNA. Or fungi have 1 set of DNA. You'll learn about that later. Okay? Okay, number 9. Thalassemia. This is mixed genetics, so this is actually an example of just simple autosomal. Okay, so it says thalassemia is a type of anemia. It's controlled by a gene. A homozygous person will have thalassemia major, which is fatal. Heterozygous will be mildly affected. So if an infant has thalassemia major, so you have a child that has thalassemia major, right? That means they have 2 what? So let's say this is not sex length. So let's say this is normal and this is disease. So if an infant has thalassemia major, what must they have? Yep. By the way, how do we know this is recessive? It doesn't say it in the question, right? But you know it's recessive because look, if you have 2 copies of it, you have a disease which kills you. But if you have 1 copy of it, you're mildly affected. This has to be recessive. It doesn't make sense if it's dominant, right? Because if it's dominant, if you have 1 copy, you're still going to have the disease, right? So this is recessive. So if the child is little n, that means the parents must be what? What must the parents be? Why can't the parents be this? Yeah, they would have, because look, almost fatal, always fatal in childhood. So it's most likely they're not going to have had 2 copies of it. So if they're carriers, I'm actually a little bit reluctant to call them carriers because remember I defined a carrier as something that has the allele and you see what? You see like nothing, like no signs, right? But it actually says you have some mild like affliction, right? So that's okay. We'll still call it a carrier. So this is normal. This, okay. I'm glad you brought that up. So this is actually probably a better definition would be blending, right? The inheritance pattern is still the same though. Still you have 2 alleles, right? So we can still describe it this way. But I would, yeah, this is actually more of a case where it kind of looks like it's blending because you are mildly affected. So you do see signs. Yeah, very good, Pam. Very good. So what are the chances that a child will have thalassemia major? Yep. 1/4, right? 1/4 for major. And what are the chances they'll have minor? Yep, 50%. 2 out of 4 is for minor. Okay? Yeah. Actually, the whole thing about blending, this is actually a good point. I'm glad you brought it up. The whole thing about blending, it's really interesting. Is if I was to ask you about sickle cell anemia, how did I define it? How did I define it? As dominant or recessive condition? Right. And if you're heterozygous, what do you see? Do you see disease or no disease? But you know what's interesting though is, what would happen if you were to look at, because in that case, we're looking at the individual, right? What would happen if I said to you, let's look at their blood? What would you see? You would see normal hemoglobin, but you would also see effect. So you would actually see both. So that would be what then? That would be not blending. When you see both, it would be codominance. So sometimes it depends on how you look at the situation, right? Don't worry. You don't have to worry about that on your test, okay? Don't have to worry about that on your test. All right. I'm not going to do 10 because, yeah. 10, what do you think 10 is?
No, stop.
I'm going to stop. I'm asking you, what do you think it is? This is an example of what? It is because this gene affects the color in the other gene, so that's epistasis. And then you have this question where you get something pink from red and white. What is that? That's blending. And then here is a question about whether possibilities. So whether or not you could have the following children. You got to figure out which ones are adopted by the blood type. So I'll leave these up to you guys to go over, okay? So let's stop there because that was quite long. That is the